So yesterday we solved this question where we said in a deck of 52 cards, 3 cards are randomly chosen. Find the probability that all 3 are aces if we were seeing the second part. The cards are not replaced before selecting the next card, right? So in that case, when we did not have replacement, we said they are not independent of each other, and we talked about how the probability is going to be dependent on what the outcome of the previous selection was. And we said then probability of selecting all 3 aces is going to be, the branch will multiply 4 by 52 into 3 by 51 into 2 by 50. Now the other way we can solve this is using combinations. We can say probability of selecting 3 aces is going to be that there are total 4 aces in the deck. So I'll say 4 C3. I am selecting 3. Out of those 4 aces, I am selecting any 3. And out of 48 non-aces, I am selecting 0. I am not selecting any from those 48 non-aces. Upon total out of 52, I am selecting any 3. This will give you exactly the same probability. We can find that out. In our calculator, we can directly calculate the combinations. Okay, otherwise if I say 4c3, 4c3 is going to be 4 factorial by 3 factorial 1 factorial, right? You can definitely solve it like this, but you directly have combinations here. If you see just above this division button in yellow, there is NCR written. So that is nothing but combination. Okay. Now if we want to evoke anything written in yellow, we'll press the shift button. Okay, the shift button, when we press, we can get everything written in yellow, and anything that is written in purple here we can get by pressing alpha button. These are the special buttons, and that will help us get those special characters. So like here, if I want 4c3, I'll say 4, then shift, and then division button. So I get a C and then 3. When I press equal to, I get 4. 4c3 is nothing but 4. Similarly, if I want 52, shift C, so I have combination 3 is equals to this. This is 52c3, 22100. Okay. You can also get permutations. With the multiplication button, you can see permutations here. So if I want, let's say 52p, I'll press shift and multiplication button, I'll get a p. So let's say 52p3 would be this. So you can get permutation combination directly. You also have factorials. You will see that above x raised to minus 1, you have factorials here. You can get factorials also. Like if I say 4, shift, and I press this button, I get a factorial. 4 factorial upon 3 factorial into 1 factorial, and that is going to be 4. Right. So if required, you can find factorials also. Otherwise, we directly have combination. So here if I say fraction 4 shift C3 upon 52 shift C3, I get this, that is 0.000181. And you can see we get directly the answer here. So if we are finding a combination, then we will use combination. If we are finding a permutation, that means if we are finding an arrangement, then we will use permutation. That means if I say, let's say I want to find this permutation. This permutation means if I say probability that card 1 is ace, card 2 is not an ace, and card 3 is ace. This becomes one permutation only. Okay, this is one specific arrangement where the first card has to be ace, the second card has to be not ace, and the third card has to be ace again. So of course, if I go by this tree diagram, I will have 4 by 52 into 48 by 51 into 3 by 50. This is how I will get the answer. But let's say if I do not if I find it without making the tree diagram, I will write permutations. So in permutation, now I have 2 aces here and 1 not an ace. So I'll say out of 4 aces, I need 2 and then arrange them in one particular order. That is why we are using permutations. And out of 48, I want 1, 48p1 upon 52p1 or 52p3. Out of the total 52 cards, I am selecting any 3 of them. So again we can use the permutation here. Four, then shift P3 into 48 shift P1 upon 52 shift P and then 3. Okay, sorry, I made a mistake. It should be 4p2, right? 4p2. Now see, if I made a mistake, I can use the arrow keys to navigate to wherever I have made mistake. I can delete this and I can press 2. So equal to the value that I get is 0.00434. Let's say this is our answer. Okay, so this is one single permutation. Okay, this is one single permutation, that the first card has to be ace, second card has to be not an ace, and third card has to be another ace. But if I want that probability that I will get 2 aces and 1 not an ace, if I want 2 aces and 1 not an ace, then I have multiple ways of doing that. One is of course this, 2 aces, 1 not an ace. The other would be this. This is another combination where I have 2 aces and 1 not an ace, and the third combination would be this. Okay. Rather, if you find the probabilities, all 3 permutations will have exactly the same probability. You have 4 by 52, 3 by 51, 48 by 50. Okay, and here you will have 4 by 52, 48 by 51 and 3 by 50. If you see multiply these, you will find that they are exactly the same probability. But what happens is I will have to add them up. So this will actually be probability C1A, C2N, C3A, this is one of the cases, plus we'll have probability C1A, C2A, and C3 is equals to N, plus C1N, C2A, C3A. These are the 3 combinations that we can get, or 3 permutations we can get to get this combination, 2 aces and 1 not an ace. Okay, but instead of finding them using a tree diagram, we can directly use combinations. Okay, this will be also equal to, I want 2 aces, so out of 4 aces I will get any 2, and out of 48 non-aces I will get any 1 non-ace, upon out of 52 cards I'll get any 3. This is how we can get the combination of all of these 3. Okay. And first of all, let me show you, this is what the permutation we got if I multiply it by 3, because as I said, all of these 3 are exactly the same. This is what we would have got, 0.01303. Okay, this is what we would have got. Now let's check, do we get the same answer using the using the combinations? So I have 4 C3 into 48 C1, again 4 C3, it's 4 C2, okay, and then upon 52 C3. You can see it's exactly the same probability. Okay. So whenever we have a sum of without replacement, then either we will do, we will use permutations or we will use combinations. Okay. I'll write down a question. In a conference, 20 actuaries and 30 accountants are in attendance. A group of 5 people are chosen at random. Find the probability that 3 actuaries and 2 accountants are chosen. Okay. Now here again, what happens is, as soon as we choose first person, there are total 50 people. As soon as we choose the first person, the total number of people goes to 49. We are not going to replace the first person and choose that person again. It's not possible. So such questions where we are talking about human beings or living, or livestock or something like that, choosing a group in random, we will have a case of without replacement. Okay, we will always have the case of without replacement. So when I'm choosing, the probability is going to change. So these are dependent on each other. This is not independent. As soon as I choose the first, if I choose an actuary, probability of choosing an actuary would be 1 by 20. I'm choosing 1 out of 20 people. But let's say I have chosen an actuary in the first choice. In the second choice, 20 by 50. 20 actuaries out of total 50 people. That is how we would be, that is what the probability of choosing an actuary would be. But if I chose an actuary in the first choice, for the second choice there will be only 19 actuaries left out of 49 total people. So clearly the probabilities are dependent on the previous choice. If the actuary has not been chosen in the first one, I will have complete 20 actuaries to choose from out of 49 total people. Okay. So anyways, we will use combination. It will be very easy. We will say probability. We are choosing the combination of 3 actuaries and 2 accountants. So out of 20 actuaries, I am choosing any 3. Out of 30 accountants, I am choosing any 2. Upon out of 50 total people, I am choosing any 5. So this becomes a combination. So did you understand? Okay. Next topic, law of total probability. Now for this we will have a few assumptions. Okay, just give me 1 minute, okay? Okay. So we are saying let there be n mutually exclusive and exhaustive events E1 to En. Okay. When I say mutually exclusive events, that means they do not have anything in common. So I'll say probability E1 intersection E2 will be same as E2 intersection E3 and all such combinations. Okay. Till let's say last one, I will say probability En minus 1 intersection En. These should all be 0, all possible combinations. Okay, there should not be anything in intersection between them. We can write it in terms of okay, I is going from 1 to n and j is less than I. Okay, the main reason we are writing less than I and not j is less than or equal to, first of all they should not be equal, because if I say E5 intersection E5, that will be E5. We don't want that. So we want intersection between two different events. Okay, so then I have taken only less than is simply because I am saying E5 intersection E4 will be same as E4 intersection E5. So I am just taking one of them, I don't need to take both of them. So that is why we have said j is less than I. Then we are saying they are mutually exhaustive events. So mutually exhaustive, that means together they should make up the whole universal set, or probability E1 union E2 union till En will be equal to 1. They make up the whole universal set. Okay, or you can write this as union I going from 1 to n Ei will be equal to 1, similar to summation. Okay, if we had additions we would have written summation. We can write union or intersection in the same way. Okay. Now simply I can make a simple diagram for representing these independent and mutually exclusive and exhaustive events. So let's say I am representing this as E1, this as E2, and so on. This last one is En. So this way you can see that there is nothing in common between them. I am not having anything in overlap, and they are completing the whole universal set. They are completing the whole universal set. Okay. Then I will take an event that is A, that has some outcomes from these events. This is my event A. Okay. Now law of total probability says, okay, before law of total probability I should have talked about conditional probability. So we will have to talk about conditional probability and then come back to law of total probability. My mistake. Okay, so just leave 2-3 lines here. Okay, maybe let's say 6 lines, 7 lines, and then let's just write conditional probability first, then we'll have to come back to law of total probability. Okay, then I'll explain the law of total probability again. Okay, conditional probability. Then conditional probability, we write it as A straight slash B. Mathematically it is something like this: probability of A intersection B upon probability of B. We'll read it as probability A given B. We'll read this as probability A given B. Okay, so we are saying conditional probability, that means we already know that B is given. What is the probability that A would occur? Okay, that is what this conditional probability occurs. Let's say I'll give you simple example. If I ask I'm saying a card is randomly selected from a deck of 52 cards. Find the probability that the card will be a 7 when we already know the card is a club. So I'm saying I saw the card and I said it is a club. Now what is the probability that it will be a 7? What are the chances that it will be a 7? So you might say that there are total 13 clubs and the card can be only one of those 13 clubs, right? And only one of them is going to be a 7. So clearly the probability must be 1 by 13, right? There are only 13 clubs and only one of them is a 7. Okay. So this is what your answer would be, 1 by 13. Okay. Let's find that using conditional probability. So again, if I say A card is 7, B card is club, probability of A will be equal to 4 by 52, probability of B is going to be 13 by 52, and probability A intersection B is going to be 7 of clubs, and there is only one such card, that is 7 of clubs. That is why it would be 1 by 52. If I want to find probability A given B, that is probability that the card is a 7 given it is a club, would be nothing but probability A intersection B upon probability of B, 1 by 52 by 13 by 52, and we are getting the answer as 1 by 13. Okay. So this is how we will calculate the same thing mathematically, right? Okay. So this is conditional probability. We are going to use conditional probability a lot throughout our CS1 course. So we are saying finding the probability of A given B has already occurred. Okay. So let's get back here. Law of total probability. In law of total probability, we said we have n events that are mutually exclusive and exhaustive events. That is why I draw this. I said they are mutually exclusive. That means there is nothing in common between them. And they are exhaustive. That means together they will make up the whole universal set. And then there will be an event A such that it takes some outcomes from these events. Going outside. Okay, so this is event A. If I want to find probability of A, okay, if I want to find what is the probability of this event A, I might say that it is nothing but this portion plus this portion plus this portion plus this portion. I can add them up one by one, right? I can add each one of these parts one by one, and this part is nothing but probability A intersection E1. That would be intersection between A and E1. Similarly, this part is going to be A intersection E2, and so on. Last part would be probability A intersection En. So if we add up all of these parts of A, I should get nothing but probability of A. Now we'll use the conditional probability. We said probability A given B was probability of A intersection B upon probability of B. This is what we wrote for conditional probability. So I can say that probability A intersection B would be probability of B into probability of A given B. Okay. So here I can write it as probability of E1 into probability of A given E1 plus probability of E2 into probability of A given E2, and so on till probability of En into probability of A given En. And finally we'll say probability of A is summation I going from 1 to n probability of Ei into probability of A given Ei. This is law of total probability. Right now we have just derived it. With an example, I'll explain what does this actually mean. Okay, this is the formula for law of total probability. Okay, now let's take an example. So this is our example. There are 3 bags containing white and black balls. The first bag is twice as likely to be chosen than the other 2. The first bag contains 7 white and 3 black balls. Okay, so let's say this is my bag 1, 7 white, 3 black. Then second bag contains 5 white, 5 black, and the third bag contains 3 white and 7 black. Now in total you can see we have 15 white balls and 15 black balls. Can you just tell me what should be the probability of choosing a white ball? If we have 15 white and 15 black, what do you think should be the probability of choosing a white ball? It should be half, right? Because half of them are white, half of them are black. Okay. So if we had just one bag in which we had 15 white and 15 black balls, then probability of choosing a white ball would have been half, and that would have been fine. But now we have more complications. We have 3 bags. If you go to bag 1, then probability of choosing a white ball would be 7 by 10. If you go to bag 2, the probability would be half, and if you go to bag 3, the probability would be 3 by 10. So the bag that you choose would influence the probability of getting a white ball, right? So in total, if I want to find what is the probability of choosing a white ball, I will have to take into consideration the probabilities of choosing these bags as well. So first of all, we said the first bag is twice as likely to be chosen than the other 2. Okay. So let's say I will name it as E1, E2, E3. Okay. So first bag, that is probability of E1, probability that we'll choose the first bag, is twice as likely as the second one and twice as likely as the third one. So clearly 2 and 3 have equal probability. So I can say probability E2 is equals to probability E3. That would be equal to, let's say, P. I've named it P. So my probability of E1 would be clearly 2P. And total probability has to be equal to 1 because there is only 3 bags. There are no other bags. So probability of E1 plus probability of E2 plus probability of E3 will be equal to 1. So that is 2P plus P plus P. 4P is equals to 1. So clearly P is equals to 1 by 4. So now I know probability of E1 will be 2 times that. So that is half. Probability of E2 would be 1 by 4 and probability of E3 would also be 1 by 4. So now I know the probabilities of choosing a bag. Now if I chose a particular bag, then what is the probability that I'll choose a white ball? So if I chose bag 1, the probability that I will choose a white ball would be 7 by 10 because there are total 10 balls and only 7 of them are white. So it's a probability of choosing a white ball given I chose the first bag. Okay, so whenever I'm saying if I chose the first bag, okay, so that is the given information. So if I chose the first bag, probability of choosing a white ball would be 7 by 10, or I'll just write 0.7. Similarly, if I chose the second bag, probability of choosing a white ball would be probability W given E2, and that would be 0.5 because 5 white balls out of total 10 balls. And similarly, probability that I'll choose a white ball given E3 would be 0.7 because 3 white out of 10. Now, using this information, we can find now probability of choosing a white ball. Using law of total probability, this is what we'll get. Now, what does this mean? We are saying that if I want to choose a ball, first I will choose a bag. So I'll say first, if I choose bag E1, probability of that would be this much. And then if I have chosen bag 1, I will choose a white ball. Probability of that is this much. These two should happen together to give me a white ball. Or, whenever we use or, we'll have plus, we'll add up the probabilities. So these two should happen together. These make up one single case. We'll choose bag 1 and then we will choose white ball from that bag 1. Here again I am choosing bag 2 and from that bag 2 I am choosing a white ball. But these are alternatives of each other. Either I will choose bag 1 and then choose a white ball, or I will choose bag 2 and choose a white ball, or I will choose bag 3 and choose a white ball from bag 3. Right. So these are all alternatives. So whenever we have alternatives, we add the probabilities. So we are getting probability of choosing a white ball as 0.55. Right. Previously when we said we had 15 white and 15 black balls, we said probability of choosing a white must be half, that is 0.5. But then we complicated. We said we cannot directly choose a ball. They are kept in 3 different bags. Each bag had a different probability of being chosen. Each bag had a different number of whites and different number of black balls. So these kind of complications change the probability of choosing white. Okay. Now this is what the statistics is all about. If I had to make a decision of whether I should go for white or whether I should go for black, the probability 0.55 is not a very big difference compared to probability of 0.5. They are almost at the center. Okay. You can say out of 100, 50 times I would have got a white. Here I am saying out of 100, 55 times I would get a white ball. It does not make a very big difference. But you can see the calculations were pretty lengthy, right? We had to calculate so many different things. We had to have a lot of information. We had to get that information and use that information to calculate to get to this. And maybe that will not make a big difference to my decision that I am going to make using this information. Okay. So what happens is, in statistics we are always debating that how much complication will give us how much accuracy. So this is giving me more accuracy than this, but it was more complicated, so the complications has increased. So more complications might lead me to a more accurate answer, but do I need that much accuracy? Because here I could have done more complications. I could have said that the white balls are always sitting above the black balls, therefore probability of choosing the white ball is higher than probability of choosing a black ball. That becomes more complicated, right? If I say white balls are twice as likely to be chosen than black balls, then that becomes more complicated. I'll get more accurate answers, but the complications becomes much larger, the calculations become much larger. So we will always have to find a balance between the complication and accuracy. The more complications will give me more accuracy, but more complications is not a good thing. Okay, so in statistics we are always trying to find that balance. How much complications will give us the maximum accuracy, and after that we may not need that much more accuracy. Okay. Whenever we are talking about models, we broadly categorize the models in two types of models. We say we have mathematical models and we have statistical models. Okay. In mathematical models, you will have something like solar system. What I am saying, solar system, how the earth revolves around the sun and how moon is revolving around the earth, how earth is rotating, all of these will come into a mathematical model because they are going to do the same thing for many thousands of years. Okay, so I can predict the position of earth, position of moon, position of sun very accurately, and that is why we can predict where a solar eclipse is going to be, where a lunar eclipse is going to be, and exactly at what time we are going to find those eclipses, right? Because that solar system, we have understood the model of solar system, we have created all the formulas that are required. Rather, Newton did almost 150 years ago. He made those solar system models that we still use, and they are very accurate. We use those Newton's formulas to actually go to the moon. But if by any chance you know the last moon mission or Mars, right? Indian mission has gone to Mars as well. Both of those missions were delayed because of bad weather. So we can manipulate and reach moon or reach even Mars. There have been NASA's probe that has gone beyond the solar system as well. We can predict exactly what they will do, when they will do, where they will reach, but we cannot predict the weather on this earth. Because it is a statistical model. In mathematical model, we will not have anything random, no randomness. No randomness. That is why they are called as deterministic model. Okay. Deterministic models. Because we can perfectly determine what would happen in the future, we can predict it, and the more accuracy you want, the more complications you will take. Okay, so the best model would be the most complicated model in a deterministic model. But when it comes to statistical model, there is some randomness. Some randomness. Okay. Some people believe the randomness comes because we don't understand all the elements of it. Like in weather, some people believe that if I know exactly all the things that are affecting the weather throughout the earth, exactly, everywhere on the earth, if I know perfectly, I'll be able to make a model to predict the weather perfectly. Then it will become deterministic. That is what some people believe. The problem is we cannot get that much data. We cannot have every point. Okay, you will need temperature, humidity, wind speed, wind direction, then currents, ocean currents, wind currents. There will be so much data for every point on the earth. It will be almost impossible for us to get that data, and if we got that data, analyze it in time to give you the answer. Okay, so what happens is we assume that there is some randomness. There are some things that we will not be able to perfectly predict, and that is why these are statistic or stochastic models. We call them as statistic models or stochastic models. Okay, they have difference. We'll not go into what difference that is. You are going to learn stochastic models in CS2, so you'll understand that later. Okay, so what happens is we assume that there is something in random. We'll not be able to predict that thing. So even if I have 100% information, I will never get 100% accuracy in my prediction. Like if I give you all the information about a coin, that let's say probability of heads is perfectly balanced, and that is why probability of heads is 0.5. I will tell you how am I rotating how fast am I flipping the coin. I will tell you, what's the wind speed, how many rotations will it take, how it will fall down. Okay. So maybe you can predict perfectly whether you will get a heads or a tails. But there are some people that believe that there is randomness in nature. There is inherently randomness in nature that we'll never be able to predict. And if that is the case, wherever we see randomness, we'll have to use either statistical models or stochastic models. And in that case, we will have to use probabilities, and we'll never be able to perfectly predict what would happen. Like here, I am able to predict that probability of getting a white ball is higher than probability of getting a black ball. That I could predict. But still, that does not guarantee that I will get a white ball or I will get a black ball. That I will never be able to predict. It's random. Correct? Yes, if I do this experiment, let's say 100,000 times, then 55,000 times I am expecting a white ball, and 45,000 times I am expecting a black ball. This is what we get from this probability. It might still not be perfect. It might still be that 55,005 times I got a white ball and 44,995 times I got a black ball. It's close enough, but it might not actually be perfect. Okay. Because it is random. Okay, there is something random in selection in this manner. I'll not be able to predict how would you select, which bag would you choose, and then which ball will you choose from that bag. I won't be able to predict that. Okay, so that is why it becomes a statistic model. So in statistic or a stochastic model, we are always debating whether we should go for more complication or we should be satisfied by the accuracy that we are getting. Okay, so throughout the course we'll be talking about these things. So next topic, last topic of this chapter is Bayes theorem. Now we'll take all the assumptions that we used in law of total probability. Bayes theorem is trying to predict or is trying to find the probability of the path that we have chosen or the bag that we have chosen after we have already got the success or the white ball. Okay. I've written E2 because EI and E1 might look similar, so I've just written E2. There's no reason for it to be 2. This is the formula for Bayes theorem. Here, if I take the same example, in the previous question, again 3 bags and choosing a ball, we are saying find the probability that the ball came from bag 3 if the ball is white. Okay, we are trying to find the probability of the path that we took. So we are saying we chose a bag, then we chose a ball, it turned out to be white. We are trying to find what is the probability that it came from bag 3. Okay. So again, for the given information, we had probability of E1 is 0.5, that is half. E2 and E3 were same, that was 0.25, and probability of getting a white ball given E1 was 0.7. Probability of white ball given E2 was 0.5, and probability of white given E3 was 0.3. Right, this was the given information. If I want to find probability that the ball came from bag 3 given the ball was white, so according to Bayes' theorem, what we should do is, should say this is nothing but probability of bag 3 into probability of white given bag 3 upon summation of all 3 I going from 1 to 3, probability of EI into probability of W given EI. Now this was nothing but law of total probability, and we did calculate that here. The law of total probability said it was 0.55. So I'll directly use it from here. This is Bayes' theorem. This is how we use Bayes' theorem. Okay. So we are trying to figure out the path that we took. Okay. Let me know if you have any problem. Let me just open a question. Okay, see question number 7. An insurance company covers claims from 4 different non-life portfolios denoted as G1, G2, G3, G4. The number of policies included in each portfolio is given below. It is estimated that the percentage of policies that will result in a claim in the following year in each of the portfolios are 8%, 5%, 2%, and 4%. Suppose a policy is chosen at random from a group of 30,000 policies comprising the 4 portfolios after 1 year, and it is found that a claim did arise on this policy during the year. Calculate the probability that the selected policy came from the portfolio G3. So this is a simple example. This is a simple example of Bayes' theorem, because what do we have? We have these groups. You can call them as bags, right? This is your bag 1, bag 2, bag 3, bag 4. Okay. It contains these many policies: 4,000, 7,000, 13,000, and 6,000. And each of these portfolios or groups or bags, whatever you want to call, 8% in the first one are going to have claims. Out of these 4,000, 8% will have claims. Out of these 7,000, 5% will have claims. So these are the given information. You can say claims given G1 is 8%, claims given G2 is 5%, claims given G3 is 2%, claims given G4 is 4%. Now we are saying that it is found that a claim did arise on this policy during the year. So the policy that we selected has a success. A claim did arise in it. Now we have to calculate the probability that policy came from the portfolio G3. So now we are going for the path. Where did that policy came from? That's the path that we are trying to figure out. So whenever we are trying to figure out the path, it is nothing but a Bayes theorem. Bayes theorem question. Okay. So let's write down the information. So first of all, there are total 30,000 policies. If I want to find probability of G1, say 4,000 out of 30,000, so it would be 4 by 30. Probability of G2, it is 7,000 out of those 30,000, so 7 by 30. Probability G3, 13 by 30, and probability G4, 6 by 30. This becomes their probability of being chosen. Policy can be chosen in these ways from G1, G2, G3, G4. Then probability that we saw claim given the policy came from G1 is 8%. Probability that we saw claim given the policy came from G2 is 5%. Probability claim given G3 is 2%, and probability claim given G4 is 4%. We want to find the probability that the policy that had a claim came from G3. So we want probability G3, policy came from G3 given we saw a claim. This is what we want. Okay. So we'll use the Bayes theorem. One of the easiest way of recognizing Bayes theorem, given information was like this: C given G3, C given G4, and we are trying to find G3 given C. So we'll use Bayes theorem. We'll say probability of G3 into probability of C given G3 upon summation I going from 1 to 4 probability Gi to probability C given Gi. So G3 13 by 30 into C given G3 0.02 upon, we'll have to write all 4. 30 cancels out. I'll just have 13 into 0.02. What did I? 13 into 0.02 upon 4 into 0.08 plus so you can see we can make a very elaborate equation here, right? In one single go we can find the whole equation. And this is the probability that we get. So this was the last topic of this basic chapter, that is probabilities. Okay. So if we are going to use these probabilities throughout our actuarial career. Okay, so probability is the basic of the whole of statistics, and we are going to use statistics throughout. Okay. So understanding this is very important. Now in the next class, that would be in next week, we are going to see basic chapter 1 and basic chapter 2. Okay, so we have still not started the we have still not started the CS1 portion, because we need to understand these basics first, right? So if you have any questions, let me know. I can talk about a little bit about the structure of the examination. Okay. So we have paper A and paper B that you have to attempt in the same diet. That means if you are giving next April examination, so you'll have to give paper A, paper B both in the April examination. You cannot choose that April I will give paper A and September I'll give paper B. No. Paper A is written examination and paper B is R programming. We are going to learn R programming also. We are going to learn R programming. R programming is a statistical language that is going to help us apply all the statistics that we are studying in paper A. Okay. So we are going to study the concepts in paper A, and then we are going to apply it in R programming, because what happens is data is going to be very large. In paper A, while we are studying it theoretically, we will use very small data points, 10 values, 15 values, 20 values. But in real life, the data will be thousands of values. So what happens is you should be able to apply that using computers. So the programming language that is going to be helpful is R programming. Okay, R programming help us apply the statistics that we are going to learn in paper A in a practical situation. Okay. Now both papers are 100 marks. This is 100 marks. This is also 100 marks. Okay. In IFOA, you will have to write this paper on Word. On MS Word, you will have to write the examination on MS Word. So for that, you will have to learn a little bit of mathematical typing. It is called equations. We are going to teach you that as well, how to write equations in Word. But if you are giving paper from IAI, that is the Indian Institute, then the examination is MCQ based. That means in the examination you will have to solve it on paper and just choose the correct option, right? A, B, C, D will be given. You have to just choose the correct option. Does not mean that the questions are going to be just one line questions or something. They will ask you to solve similar to what we are going to learn here. It's not going to be just one line question like this. You will solve it, but you can choose this answer finally in your MCQs. You don't have to show any of these workings. You will solve it on paper and directly choose the correct answer. This whole question would be somewhere around 3 marks. Okay. So if you are giving paper from India IAI, then you don't have to learn the mathematical typing or the equations. Okay, so that will be an advantage here. Then of course R programming in both IAI and IFOA will be on. There is a software called R Studio. Okay, it's a free software. You don't have to worry about paying for it. But of course, if you are giving from IFOA, MS Word, Microsoft Word is not a free software. So either it comes with your computer directly, then it's well and fine. Otherwise, you will have to buy Microsoft Office. Okay. But R Studio is free to download, free to use. So the examination will be on R Studio. We are going to learn it on R Studio itself. Okay, so anyways, when we'll start our programming, I'll tell you how to download and install R Studio and stuff. Okay, your examination will be on R Studio. Now the paper A and paper B examination weightage is different. So in paper A is given 70% weightage and paper B is given 30% weightage. That means out of this 100 marks, whatever you score, it will be taken as 70% of your total marks, and whatever you score here will be taken only as 30% of your total marks. That means, let's say in paper A you scored let's say 85, and in paper B you scored, let's say, 65. So 70% of this will be taken and 30% of this will be taken as your total marks. Okay, so I'll have 85 into 0.7 plus 65 into 0.3. So your total marks would be 79. Okay, so this is how your final marks will be reflected. Okay, this final passing mark should be above the passing mark. So IAI has kept the passing mark fixed at 50. So if you're giving paper from IAI, this combined should be above 50. And if you're giving from IFOA, it's a variable passing mark. Usually it ranges anywhere from 55 to 65. This is usually the passing mark. So let's assume that we have to score above 65. Okay, we have to definitely score above 65 marks. Okay, chalo, any other question?
No, but no questions.
Okay, so if you have any doubts, you can contact the number given below me, right? That's the office number. You can contact that directly. He'll give you all the details. Okay, and I think we'll just have 2 demo lectures. So if you feel like you want to join CS1, you want to study with me, so I'll see you next week. Okay.
Pranay, just I have
Yes.
one doubt. If I join the classes, what should be the timing?
See, timing we would prefer something similar in the evening itself. If you feel like you have work and you come by certain time, let me know that. Okay, so we'll keep it that ways. So I would prefer somewhere around 6:30 to 8:30.
Okay.
Okay, We may shift it a little bit depending on the students,
So
yeah.
timing, the classes would be weekend or weekday?
Weekdays.
Okay, right.
Okay. So at the beginning we will have 2 days a week, and later on we might add a third day. Okay.
Yeah, sure. Okay, then fine, fine. Thank you. Thank you.
Okay.
So I will reach you on WhatsApp.
Yes. Okay. Sure.
Thank you.
Welcome. Bye.